Historically, wheels were made of metal or wood. With the invention of air-filled car tires in the early part of the 20th century, the ride was revolutionized. The inflated rubber tires could better absorb the bumps on the road, and the addition of tread gave the invention serious traction. Car tires have come a long way in the last century. The modern summer tire is made of 10 to 15 different components, which include natural and synthetic rubber, chemical additives, and carbon black, a pigment. Giant blenders mix these ingredients under heat and tremendous pressure. There are various formulations for different parts of the tire. In each case, the result is gummy rubber dough, which machinery then rolls into sheets to await further kneading and processing. Polyester fabric unrolls into a machine called a calender. The calender is equipped with rollers that apply warm rubber to both sides of the fabric. This produces a rubberized fabric that will be used to reinforce the tire. This fabric ply is needed because rubber alone isn't sturdy enough to make a tire. Numerous cotton cords now spin off bobbins simultaneously. Machinery pulls them onto the warm rubberized fabric. They land on a bit of an angle and adhere. This cording creates channels that provide pathways for venting air during the actual tire building. Making rubber for tread requires 3 different rubber formulations. Extruders shape the 3 streams of rubber, and then they enter a die that forms them into one. Many paint rollers apply different colored stripes. It's a coating system for identification of the ingredients during processing. To avoid tension, the system creates slack in the feed. A blade slices the tread rubber to length. Next, many steel cables uncoil at once to make the bead, the part of the tire that gives it the strength it needs to stay on the wheel rim. Machinery arranges the cables in the desired configuration and encases them in rubber. More equipment rolls the bead material into hoops, sized to fit the wheel rim. They're now ready to build the tire. Using a special rotating drum, a worker arranges the 2 bead hoops on it. Next up is an airtight piece of rubber that will act as an inner tube, followed by the corded ply. Inflated bladders roll the rubber around the bead on both sides and then retract. A server applies sidewalls to the beads. Little rollers fold the sidewalls over the beads. This completes the inner part or skeleton of the tire. They assemble the outer layer separately, beginning with strips of rubber embedded with steel cord. The system wraps this rubber around a second tire building drum. Next up are narrow strips of rubber ply. The computerized system winds them with just the right amount of tension for a graduated effect. They're now ready for the last layer, the tread rubber. Machinery applies it to the ply. It's time for the 2 tire fabrications to become one. A transfer ring collects the assembly and transfers it to the inner part. Compressed air inflates the tire to shape it, and all the sticky layers adhere together. The machine rolls the edge of the tread rubber over the sidewalls. They now have what's known in the industry as a green tire, an uncured tire without tread pattern. Next, it's into a mold to bake and shape the tire. The 2 parts of the mold come together like a waffle iron. Inside, hot steamy bladders expand to shape the tire and transfer the tread pattern to it. This specific tread pattern is designed for summer tires. This cutout of a car tire demonstrates how all the layers have been fused together. The time in the hot pressurized mold has caused the rubber to vulcanize, a chemical reaction that transforms it from a weak and sticky substance to one that's strong and elastic. A worker trims excess rubber. After final inspections confirm the tire shape is uniform and geometrically correct, the tire is ready for shipment. It's time for the rubber to hit the road. Cavemen sharpened pieces of flint and used them to shave their facial hair. Modern man can simply go purchase a pack of razor blades for his shaver. While several styles of shavers and blades exist, many men believe the traditional type of razor blade gives the closest shave of them all. They're paper thin, yet sharp enough and strong enough to cut through the coarsest beard. Razor blades are made from a stainless steel strip that's a mere 4/1000th of an inch thick. The strip first enters a punching machine that stamps out the overall blade shape. These dull-edged blades to be are called blanks. At this stage of the process, the stainless steel is very soft, as pliable as paper, so they now harden and strengthen it through a 4-step heat treatment process. Step 1. They heat the blanks in a furnace to just over 2000 degrees Fahrenheit for about 30 seconds. Step 2. They briefly submerge them in cold water. This is called quenching. Step 3. They chill them for about 20 seconds in a deep cooling chamber at a temperature of -58 Fahrenheit. All this progressively restructures the molecules, hardening the metal. However, the metal becomes brittle, necessitating reheating the blanks for 20 seconds. The now hard blanks then move through a printer, which applies the razor blade brand name. Gas flames instantly dry the wet ink. Now it's time for the blanks to become blades. They enter a grinding and polishing machine. Within it are 3 grinding stations which first sharpen the contour, then produce 2 super sharp cutting edges. The blades then pass through a polishing station that removes burrs left by the grinding. Until now, the blades have been connected to each other. As they exit this machine, a knife separates them. The factory's quality control lab pulls samples from the production line and checks, among other criteria, the quality of the grinding and geometrics of the cutting edges. Then, every single blade the factory produces is examined for cutting-edge defects. Technicians assemble blades in packs of up to 800, then shine fluorescent light on the 2 cutting-edge sides. This makes defects visible. Blades that pass this inspection are washed with solvent to remove contaminants, then dried. The now pristine razor blades go into a vacuum chamber. It draws a chromium-based coating onto the surface, rendering the cutting edges harder and more wear-resistant. Next, spray nozzles apply a non-stick coating which will help the blades glide smoothly over the skin. To adhere the coating permanently to the blade surface, they bake it on for 20 minutes at about 660 degrees Fahrenheit. Quality control technicians test samples again, this time to ensure the blades meet strength specifications. This test machine measures the force required for the blade to cut a thick wad of wet paper to a certain depth. Back in production, workers submerge the razor blades in organic oil for about half an hour. This provides additional protection against corrosion. On the packaging line, the equipment wraps each blade individually in wax paper. The wax coating on the paper helps protect the razor blade against corrosion during storage. Wax paper is also stronger than regular paper, so the blade's razor-sharp edges don't cut through it. The edge of these razor blades are about 10 times thinner than a human hair. A blade typically lasts about 6 shaves, so the average male goes through quite a few, considering that over the course of his lifetime, he'll have spent more than 3,300 hours shaving his face. food just slides off nonstick cookware's remarkably slippery surface. In 1938, an American chemist was experimenting with refrigeration gases. A waxy substance formed. Years later, when bonded to cookware, it gained a nonstick reputation. When it's time to fry, using a nonstick pan averts a messy situation. The nonstick coating is one of the slipperiest solid materials on Earth. Called polytetrafluoroethylene, the name is a bit of a mouthful, but the appeal is simple. Food won't get stuck on this non-stick surface. To make the aluminum pan, they use 70% raw material and 30% leftovers from prior production of pots and pans. They fire it to a molten state and filter it to remove contaminants. The liquid aluminum flows into vertical rectangular molds. A jacket of water around the molds cools the aluminum to take it from a liquid to a solid. A crane extracts the cast slabs. They're heading to a heating chamber to soften the slabs. This will allow the metal to be shaped and formed. A saw slices the slabs in two and trims the ends. More blades scrape the top and bottom to remove impurities. A conveyor repeatedly feeds the shorter slabs to heated rollers. Guides at the side maintain the width, while the rollers compress the aluminum, taking the thickness down to about 0.2 of an inch. The rolling also elongates the slab substantially. It starts out at 6.5 feet long, and after a few minutes of rolling, it's been stretched to well over 100 yards. Pizza cutter-style blades trim the edges of the aluminum sheet. Another roller winds the aluminum into a big coil. They then unwind it and squeeze the aluminum to flatten it. Machinery now pulls the long aluminum sheet forward to a 132-ton punch press. This powerful press forces the metal around a frying pan-shaped die and then punches out the shape. The freshly formed aluminum frying pan falls onto a conveyor below. The leftover aluminum will be used to make new frying pans. The pans now ride a conveyor through a washing station, where they're cleaned and then treated with sodium hydroxide. This opens the pores of the metal to allow an enamel coating to stick to the outside and the non-stick finish to adhere to the inside. A worker inspects the pans and places them upside down on spray fixtures. It's a tight fit to shield the inside from the enamel spray that comes next. The pans spin on the fixtures and twirl by the spray nozzles for an even application of enamel to the exterior of the pans. A clear glossy coat follows. The frying pans transfer to a dryer conveyor. The hot air pulls out water from the enamel coating, and the color goes from gray to chalky white. An automated squeegee silk screens the company's name and other information onto the pan bottoms. They now enter a long curing oven heated to 1040 degrees Fahrenheit. The cure toughens the enamel, deepens the color so it turns gray again, and it adds gloss. A such-thing device picks up the pan and turns it around for the inside coatings. A sprayer applies a special primer that will make the non-stick coating adhere to the pan. It then applies the non-stick coating. The pans receive 2 layers of this non-stick synthetic substance. The suctioning device releases the pan and it lands upside down. Then the pans journey through the oven again to cure the non-stick finish at around 800 degrees Fahrenheit. On exit, water rains down to cool the pans and rinse off any contaminants. Then they go through an infrared light chamber to dry off. From a plain shell to a pan with an enamel finish on the outside and a non-stick coating on the inside, the transformation has taken just 1 hour. A worker now aims a laser and aligns it with lettering on the bottom, allowing him to punch holes in a precise location on the side of the pan. He slides pins into the holes and slots them through holes in the handle fitting. Using a ram, he flattens the pins to rivet the handle to the pan. Now, no matter what's cooking, cleanup should go smoothly. The origin of facial tissue may be Japanese. A 17th century historical account describes Japanese blowing their noses in small soft papers, then throwing them on the ground. Modern-day tissues were first marketed in the early 1920s as a disposable cloth for wiping off cold cream. While some sneezers still prefer traditional cloth handkerchiefs, the disposable paper tissue is the implement of choice with the sniffling and lens cleaning meshes. This brand is made entirely of recycled paper, specifically used computer printer paper, because its short, flexible fibers produce soft tissue. The half-ton bales go into a giant machine called the pulper. It breaks up the paper into fibers and mixes them with water. The result is called pulp. Next, it injects the pulp with air. This causes the ink to detach from the fibers and cling to the air bubbles, which rise to the top and drain off. The machine then feeds the now ink-free pulp through several rollers. Like an old-fashioned wringer washing machine, the rollers squeeze out the dirty water. A screw conveyor then breaks up the pulp and moves it to the next station, which rinses it with clean water. Now the pulp is ready to become tissue. That transformation begins in the paper machine. It injects the pulp evenly across a screen conveyor belt. Then the pulp passes through rollers that press out the water. The extracted water drains down through the screen. The pulp then passes through a hot air dryer and exits the machine as a thin 10-foot wide sheet of paper. Each jumbo roll coming off the machine contains about 37 miles of paper. The converting machine is the giant contraption that now transforms this paper into tissues. The first station unwinds 2 rolls of paper, applying modest tension to remove waves and wrinkles. The next station mates the 2 papers, producing a 2-ply sheet. The following station holds the sheet steady with suction, as a knife slices across it every 8.5 inches. You can see the cuts in slow motion. At the next station, these 2-ply sheets meet up with 2-ply sheets coming from the opposite direction. Here's what that looks like in slow motion. And at full speed. The sheets enter a mechanism that folds them in half, in an interlocking fashion. In slow motion, you can see how they interlock. Each sheet folded in half, one side inserted into the fold of the next sheet. This happens at a speed of 16 folds per second. This produces a huge stack of folded tissue 5 feet wide. The next station separates the big stack into small ones, in preparation for the final cutting. Each smaller stack contains the precise number of tissues the tissue box will contain, from 80 to 250 sheets, depending on the format they're packaging. The smaller stacks now travel to the next station, where an automated circular saw cuts every 8 inches, producing the final tissue size. The interlocking folds ensure that when you pull out one tissue, it draws the next out of the box ready to use. To produce 3-ply tissues, the converting machine processes 6 rolls into 2 sheets of 3 plies each, then folds them in the same interlocking fashion. The finished tissues travel by conveyor belt to the automated packaging line. A robot with multiple suction-cupped arms grabs flattened boxes one at a time, opens them, and lines them up on another conveyor belt running alongside the tissue belt. An automated arm compresses the tissues and slides them into the box. The next station glues the flaps closed. The top of the box has a removable tab with clear plastic film underneath. A tight slot in the film makes grabbing a single tissue a non-issue.
Thank you for watching at Ronnie's Mind Palace. We talks everything. Never boring. God bless us all always.